pick up where we were last time, I debated keeping all this stuff about elemental cycling and how these elements are used in the basis of food production, right? Because this isn't explicitly biochemistry; it's more biogeochemistry, is what you would consider this to be, which is how elements cycle through the ecosystem, specifically in this case, the food chain, right? But the thing that I think I want to give you the broader perspective on why I'm going through each of these, first of all, and that is because I want you for a moment to think. So our president right now, what's his name, Donald Trump, he is, how old is he? He's 73.
What? I thought it was something.
No. He's like 73, 75. How old is he? No, I don't know if he's 77. I think Bernie Sanders is 77. I think Donald Trump, he's 72. Yeah, right. But the point is, I want you for a moment to do a little math in your head and think about what year you will be 72 in. Think about that for a moment. Okay? Well, you can keep it to yourself. It's okay. But think about that year, right? Think about that year that you're going to be 72 in. That's probably the year like 2048, 2050, something like that. I'm imagining for all of you. More? No, 2070. That's right. Sorry, I couldn't do the math. 2070. In the year 2070, the planet is going to be really different than it is now. Really different. We have had on average, warming of the planet by 1 degree since pre-industrial times. This is not a political statement. This is a statement of fact. This is scientific fact. And so one of the things about this class that I want you to be able to do is to be able to divorce political perspective from your ability to scientifically assess fact, right? So the way it's supposed to work in a civil society is that we have an agreed upon set of objective measures or facts, and then we can disagree about how to address them. Maybe, this is where differences in policy come into play. But I am here today as a science teacher to help defend the notion of scientific fact. And it is a fact that the planet has warmed by 1 degree since pre-industrial times. It is also a fact that the best models, all signs, all scientific, by scientifically sound objective measures, that by the time you guys are the age of our current president, our planet will have warmed an additional 0.5 degrees centigrade to 1.5 degrees centigrade. So a total of 3 degrees centigrade by the time we get to the year 2070. That will have profound impacts upon all aspects of life on Earth and your life. It is true that you guys are profoundly privileged to live in the United States, a country that has a lot of resources that will be able to help mitigate some of the effects of that change that's happening in the biosphere on Earth, right? We have a lot of money. We have a lot of resources. We have a lot of wherewithal to be able to secure water, right? Water is a problem. I'm going to make you guys read some literature that talks about the changes in the food system, the changes in access to water that your generation has to deal with. These aren't just abstract policy debates that happen for people who are in their 70s now. Say it's Bernie Sanders and Donald Trump debating in the next election. None of them are going to be around Neither of those two people are going to be around. This is personal for you. It's part of your life, right? And so one of the things that I want to do in this class is I'm not telling you what the solution that you should support is. I'm going to be showing you some problems that exist that are related to how we grow food, and I'm going to show you some creative solutions. I'm not presenting them as being necessarily what I think is the ultimate solution, right? But we need to have a populace, particularly one that considers themselves to be liberally educated. And I don't mean politically liberally, I mean broadly, and liberal in the sense of broadly educated. A broadly educated individual has to be able to look at facts and understand what they're seeing, okay? Even if you're not a scientist. Even if you're not a scientist, because science is the way that you measure what's happening around you, the impacts that our lives on Earth are having on the biosphere. It's so important. It's so important. I don't want you to say that I took a science class at Colby, you know, in the year 2030, 2040, 2050, you're looking back on your time in college. I took a science class, but they never, you know, told me this was going to happen. I'm telling you, change is coming. Change is happening. And these are the dynamics behind them, okay? So I'm starting with the Haber-Bosch process because in a lot of ways, Haber-Bosch is what got this ball rolling. It's what got this ball rolling. The truth of the matter is, and it's an inconvenient truth not to take a line from, this is me laughing at myself. What's his name? The vice president that lost to Bush. What was his name? Al Gore, thank you. But it is a good line. It is an inconvenient truth that there are too many people on Earth given the carbon footprint, given the resource footprint that they have. I'm not saying there are too many people on Earth, period. I'm not saying that. It's a different debate. But it's fairly indebatable that the number of people on Earth, given the footprint, the resource footprint that we currently have, if you were divided per capita, is not sustainable. It is not sustainable. And we can do better. We will do better. And the question is, what is the time course of that, right? Because the speed with which we do better is going to determine the outcome in a very real way. Okay, so this population explosion that's happened on Earth in the last 100 years is thanks in no small part to the work of this chemist here, Fritz Haber. And what's kind of interesting about this guy, and we'll have the debate in class after you guys have all read that podcast, which you can close the door so I'm not bothering people with my booming soapbox here. I'm not on a soapbox. Is this guy, Fritz Haber, so the question the podcast asks, is the world better for the presence of Fritz Haber or worse off? Is it better that he lived or worse that he lived? And this is an interesting question because Fritz Haber wasn't just responsible for making this chemical process for the fixation of nitrogen. Yeah, he developed Zyklon, which was, and he also came up with the idea of using chlorine gas in trench warfare during World War I, and which led to the death of thousands of Allied soldiers who ended up drowning in their own phlegm because they inhaled chlorine gas, nasty stuff. And then he invented Zyklon, which was the gas that was used in the concentration camps to kill hundreds of thousands and millions of people. Ironic that because he was actually Jewish himself and had relatives of his die in the concentration camps at the mercy of this gas that he had invented. But he produced this industrial process which enabled the life for literally billions of people on Earth. When he was alive, there were only about 1 billion people on Earth. There are 8.3 billion people on Earth right now. That's unbelievable. Population on Earth has never grown like that within the span of 100 years. I mean, that's 100 years ago because of this chemical process. All right, so we're gonna explore these elements and how they're used to make food, but also we're going to look at some of the downsides of them, so you can have a more nuanced view of these this biochemistry. Any thoughts? All right. I have a loud voice, but I don't want to drown anybody out. So please, you just bring it to me. It makes me happy when people do. Okay, this guy was a genius. There's no doubt about the fact that he was a genius. The problem was, how do we get nitrogen, which I showed you has the 3 bonds between 2 atoms of nitrogen. That's a high energy bond. It's really high energy. It's hard to tear apart. It's not chemically very reactive. 75% of the air out there is made of this stuff, but nitrogen fertilizer is pretty hard to come by otherwise. The principal source of nitrogen fertilizer was manure, right? Prior to this. So,
get enough manure?
Nope, there wasn't enough shit to go around. So what he realized, I told you the story of lightning, was that when a lightning strike happens, there is a bunch of nitrates in that soil. It oxidizes the nitrogen. So he basically tried to recreate this situation. This big metal tube here on the right was the first industrial reactor for the production of what's called anhydrous ammonia. And so they take nitrogen gas and they pump it into this tube, get it up to really high pressure, and they pump some hydrogen gas in there too. Get them like astronomically high pressures, very, very high pressure, and they heat it up, high temperature. High pressure, high temperature, and then they send an electrical current through it. They have an anode and a cathode on either end of this, and so you basically just have a big bolt of lightning runs through this high pressure, high temperature tube of nitrogen and hydrogen, and then out drips anhydrous ammonia, which can get bottled up and then sprayed on the ground and gets converted into nitrates and nitrites by the soil microbia. All right. So all of this nitrate out there, we could literally spend the rest of the week talking about a lot of different facets of this. We could talk about how great it is that we have all of this nitrogen that we can spray on our crops, so we have all this food. By one estimate, something like half to 3/4 of the nitrogen in your body, the nitrogen that is making up each and every one of us in this room, comes from the Haber-Bosch process. It was made in the nitrogen was fixed in some giant reaction vessel someplace. Yeah, think about that one. Marinate on that one for a minute. You are what you eat, right? Or we could talk about eutrophication in fresh watersheds. That's what my wife studies, right? She looks at nitrogen cycling in aquatic ecosystems and the impact that has on whatever, ecosystems, freshwater ecosystems. Or we could talk about its impact on drinking water, the abundance of all this nitrate in drinking water. So there are about 15 teragrams of nitrogen per year that get into our groundwater. Teragrams. Woo! So there's kilogram, right, which is about 2.5 pounds, and a megagram. Yeah, a megagram is 1,000 of those, and then a gigagram is 1,000 of those, a million, and then now we're up to a teragram, 1 billion kilograms per year. 1 billion kilograms per year of nitrogen get into our groundwater. Think about that. That's a whole lot of nitrogen, folks. That's just nitrogen. From anthropogenic sources. That means from the Haber-Bosch process, from fertilizer. A huge amount of this shit is getting in the water that we drink. And it becomes a particular problem in agricultural areas where the groundwater is very shallow. All right. So this is a public health crisis. So about 1.5 million Americans drink water that has some level of nitrate contamination. It's a lot of people. I mean, you know, that's what, like 0.5%, 0.5% of all men, women, and children in the United States are drinking poison. And why is it? Why is it a poison? Why do we call it that? Well, it causes methemoglobinemia, or more easily known as blue baby syndrome. And the reason it's called blue baby syndrome is the nitrate binds to the iron. It binds, so red blood cells bind oxygen, and the thing that binds the oxygen is the iron group, but the nitrate will change the oxidation state of the iron and make it so that the iron is not binding the oxygen. Essentially, when you have nitrate in your body, it's preventing your red blood cells from being able to carry oxygen, and that's what gives the cyanosis, the blueness in the skin, in particular babies, because they're much smaller and way more susceptible to this kind of insult. So in addition to blue baby syndrome, which is a pretty nasty thing for the children, it leads to birth defects, increased rates of cancer, decreased IQs in children who are exposed to this stuff. It's a major problem. It's a major problem in rural areas like Maine. Particularly, you see this in places like Iowa or Nebraska, the Corn Belt. All right. Here's a little map of where you're going to see high nitrate contamination in the United States. And we see, as I said there, across Oklahoma, Nebraska, basically the plain states, wherever these people are growing food and dumping a bunch of nitrogen on there. Now, I'm going to tell you something here about, well, what do we do, right? What do we do? We need crops, right? We need crops. And to grow those crops, we got to put nitrogen on it, right? Is that it's a little bit more sophisticated than that, however. Because often what happens is fertilizer companies, fertilizer is just a commodity, like anything, right? And the way it works is the fertilizer companies are selling their fertilizer in the spring, The people are buying a whole bunch of it. They're dumping it on their fields throughout the summer. And then that crop comes to harvest in the fall. And if the fertilizer companies overproduced for that year, right, they have a surplus. So the thing is, like, when you look at a commodity price, when you're looking at a commodity price, who's econ in here? Any of you guys? Oh, God, I have a whole class of economists. Frightening to me. Sorry. But I'm going to try. I'm going to wade into it. Look, when you look at a commodity price, what's dictating the commodity price? Is it like supply and demand? Is that what's dictating commodity price? It's storage. It's storage. Where do you stick the stuff? That's what supply means. All that corn, all that fertilizer, all that wheat, it's real stuff. It's got to sit in somebody's silo somewhere. Cargill or Monsanto or somebody's got to stick that crap someplace. The price is dependent upon storage. How available is storage? Because you got to pay to store stuff, right? And so, if any of these producers are sitting on a surplus, they got to mobilize it. They got to get it and liberate their storage for the next cycle. And so what happens in the fall, these fertilizer producers, they will, what would you do if you were sitting on a ton of surplus of anything? What do you do with it? Okay, there's that. Sell it. How do you sell it?
Sale.
You put it on sale. You put it on sale. You make it cheap. So if you track the price of fertilizer throughout the year, it bottoms out in the fall, right? Because demand is down, they have surplus supply, and a storage problem that they need to fix, right? Goes on sale. They basically give it away to the farmers, telling them, messaging, just spray it on the field now in the fall. It'll give you a little bump in the spring. It'll preload your fields for the spring sowing, right? The problem with that is spring runoff. Spring runoff, okay? You get the snowpack, the melt, and look here at this yellow area. What do you notice about that yellow area? What part of the country? If you had to describe that yellow area in one word besides yellow on the map, huh? Midwest, that is one word. I have a better word even. Yeah, please. Huh? It's pretty flat. It's pretty flat. Yep. It's mostly northern.
It's spreading.
I'm talking about the geomorphology is what I want. Yeah, Josh. It's the breadbasket of the country where we do a huge amount of growing there. Why do we do so much growing there? It's flat. But what else about that part of the country that makes it really good? Yeah, so we say breadbasket. This is one of two places on earth that the bread comes from. There's really only two places on earth that make all the wheat on earth. It comes from right there, and then the Caucasus in Russia, right? In the former Soviet states, the Caucasus. It's the other place that's like this. This is such an amazing resource for one reason. Well, a number of them, but one big one. What is it? It's not actually the lakes.
Everything
the Mississippi. If I was going to use one word to describe that yellow area, that's the Mississippi River Basin. That's why the bread grows there, right? Because of the historical, and I'm talking eons of inundation that has put rich, silty soil, just like the Nile River Valley, has made the Mississippi watershed such a beautiful place to grow food. All right? But that Mississippi watershed is where we have the highest application of nitrates. We're getting all that water that runs down the Mississippi. Okay, so we're going to come to another aspect of this in a moment. But before we do, I want to lighten it up here because I've been getting pretty heavy today. and we're going to switch gears to phosphorus. I want to tell you the story of phosphorus, because to understand nitrogen, you have to understand phosphorus as well. Okay? And I'll tell you the story of how phosphorus was first discovered, because it does relate to food a little bit. This guy, Hennig Brandt, was he was a Dutch uroscopist in the 17th century. And so uroscopy goes back to Hippocrates, the Greek, who would take urine, say you weren't feeling well, and Zach, you're like, something's wrong. You go to the doctor, and they have you pee in a jar. And normally, like nowadays, they like send that off and like do whatever they do to it, analyze it. But back then, they would swirl it around, hold it up to the light, see how long the bubbles stay, what's the color, how does it smell, what does it taste like, that kind of thing. So, for example, diabetes mellitus, you've heard of diabetes mellitus before. Diabetes mellitus is so named. Diabetes is a disease where you urinate a lot. Diuresis is urination. Mellitus means sweet. Like mellifluous is a sweet music or whatever. So diabetes mellitus is sweet-tasting urine because it ends up with sugar in the urine. Because these people have high blood sugar. Diabetes insipidus, a totally different thing, different disease, is insipid because the urine doesn't taste good. So anyways, this guy was a uroscopist. And it was how he made a living, right? It was like a hard knock life back in the 17th century. So you get sick, you go to this guy, he'd like look at your urine, maybe take a swig, and try to figure out what was wrong with you. But he was also an alchemist, not a chemist, an alchemist, which is sort of kind of the precursor to chemistry, but it wasn't really science. They were trying, the main goal of alchemy was to find the Sorcerer's Stone, the Philosopher's Stone. And who here does not know what the Sorcerer's Stone, the legend of that is? You guys came up in
Gotta make that gold.
The era of Harry Potter. You all know what that is. Yeah, so it is a stone that helps you convert lead into gold and then live forever, right? So you have all the money you need and you can live forever. Who doesn't want that? Well, he was searching for the Philosopher's Stone, and he needed a lab bad. He needed a lab bad. And uroscopy wasn't really, you don't make a lot of money doing uroscopy. So he married a rich woman. He married a rich, old woman, and she died. And then he got a bunch of money and a son out of that marriage. And then he did it again. He married another rich, elderly woman, and she died. Both of them. I don't know. I'm not reading into it any further than the facts. But he got a bunch of money and two stepsons out of these marriages. And with it, he built an enormous lab in his house. And then he took his two stepsons and he sent them out to the bars, the brew pubs, the beer gardens of Flanders, and retrieved as much urine as he possibly could. In fact, he gathered up 1,500 gallons. To give you a sense of that, like this room is probably, I don't know, 800, so maybe two of these rooms full of urine. And he let it in his basement putrefy for like 6 months. I mean, it takes a while to gather that much urine anyways. Let it sit and rot in his basement. And then he began to boil it down. And can you just imagine the smell and what his two stepsons shown there must have thought? So he was basically like trying to convert beer into gold, right? Who doesn't want to try to do that? And this is a little bit of his recipe here. Boil 1,500 gallons of putrefying urine down into a thick syrup. Syrupy urine. Heat that syrup until a red oil distills up from it. Draw the red oil off, etc., etc., etc. He went through all these steps until eventually he had gotten the 1,500 gallons down into a glowing golf ball, a white glowing golf ball. That was pure phosphorus. Phosphorus glows in the dark. And this is where we get the word phosphorescent.
What the hell?
Yeah, that's what he said. It's like, I did it! I found the Philosopher's Stone! The reason I'm telling this story is not to, also it's a little bit to kind of gross you out, but it's mostly to get you to understand that phosphate, the phosphate that you eat emerges in your urine, right? There's a steady state of phosphate in your body, so whatever phosphate you're bringing in your food is passing out of you in your urine, all right? And he was able to prove that fact in the discovery of phosphorus, right? Phosphorus was first isolated from beer piss. And phosphorus went on phosphorus went on to be extremely important. Not only is it important in terms of being used for fertilizers, it was also matches were made out of it, incendiary, like white phosphorus bombs, is like used even up through the Vietnam War. A lot of explosives were made out of phosphorus. So, important discovery. And of course, it is essential for all life on Earth. We need it to make the nucleic acids that are DNA, that are the backbone of our DNA. Phosphorus is an important part of the phospholipids, the lipids that make up the membranes of every single cell in our body. I'm going to go through the structure of our cells in the next set of lectures, just a little bit, so you can understand why phosphorus is important. Phosphates are an extremely important component of bones and teeth. So everyone thinks that just calcium. Well, in fact, it's the calcium-phosphorus balance in your body that enables the formation of bones and teeth. And then ATP, adenosine triphosphate. So this is like the chemical fiber of your body. It's maybe a 20. Maybe inflation's put it past the 5. If glucose is the $100 bill, ATP is the $20 bill of the whole deal. It's the molecule that is used as the energy source to drive a whole host of molecular interactions that are otherwise energetically unfavorable, but they need some energy. They get it from ATP, right? And that is this molecule on the bottom here. So you see all those ring structures with the nitrogen and all that there. And then you see the 3 phosphate groups, the PO4 groups in a chain off to the left. Those ring structures, that's adenosine, and they're attached to this tail of phosphates. What happens with that stuff, we'll talk about this later, but those phosphate groups get clipped off one at a time. They're very high energy bonds. The phosphodiester bonds are very high energy. And so when we clip the phosphates off, and we're able to use, your body uses that energy that gets released to drive certain chemical reactions. All right? So that's the basis of essentially all energy-consuming reactions that happen in your body require phosphate. Who had heard of ATP before? Most of you a little bit? Some of you? Okay. Well, phosphorus is essential to life and thus agriculture. And this became recognized early on in the 19th century. This guy Liebig came up with this thing called Liebig's law of the minimum. And this was the idea that if you're making a barrel, for example, this is the metaphor he used, if you're making a barrel, that it will only hold water up to the point of the lowest stave, all right? And so if you're trying to grow something, the growth of that thing is going to be limited by the nutrient in shortest supply. So typically, there's going to be a limiting ingredient, and we can talk about nitrogen versus phosphate limitation. So does it work? Well, it turns out that it works most of the time. Liebig's law works most of the time. Typically, the primary production of the autotrophs, aka plants, is limited by either P or N. There are some variations on this, however. So it can be co-limited by both N and P if you don't have enough of either of those together. And this is because you need more than N and P. You need various micronutrients. For example, potassium, molybdenum, silicon. Iron is a big one. They've talked about seeding the ocean with iron to get a flush of algae that can be used as a carbon sink. Whatever. All right. So here's the phosphorus cycle. I've shown you the nitrogen cycle, and we're going to talk about the phosphorus cycle because it is important. I want you to see this is all going to lead to another outcome, negative outcome from both positive and negative outcome of the production of food on Earth. So the phosphorus cycle, unlike nitrogen, phosphorus does not have a gaseous component. There's no phosphorus in the air, right? There's no gaseous form of phosphorus. And because of that, it has to move through the landscape. And that's super duper slow. We're talking geological timescale slow. So if you look at the mass of most rock, about 0.1%, so 1 in 1,000 parts of a rock are made of phosphorus. That's a lot of phosphorus. That's a huge amount, actually. It's a vast supply. But it's extremely dilute. It's very rare to find concentrated amounts of phosphorus, which is why that other podcast that I showed you, the This American Life one, about No Island is an Island, is about an island called Nauru, where it was full of essentially bat guano, bird guano, a high source of phosphate. So in 2017, last year, the United States Geological Survey estimated that 68 billion tons of phosphorus is in the global reserve. All right, that's how much that we have on Earth somewhere. And of that, about 250 million tons were mined last year, or 2 years ago, in 2016, 0.26 billion tons. So this phosphorus cycle, this phosphate that's in the rocks gets eroded with time and works its way down off the rock into the water and gets deposited in marine sediments, and then with time it gets accreted up into the mountains again. Super duper slow. It takes millions of years for phosphate molecules to cycle around on Earth. All right? So there's this slow phosphate cycle from rock to soil down into the ocean. 500 million year-long journey. But as it's passing through the soil, most of it actually never interacts with biology. It just doesn't get sucked up at all by plants or animals or anything. But some of it does. Some of it does. And this leads to what's called the fast P cycle. And this is where the problem starts. This is where we get into trouble. So this is a much shorter cycle, a little loop that happens within this larger cycle. Some of the phosphate is going to interact with biology. It's going to be taken up by the primary producers, the autotrophs, which then get eaten by the heterotrophs, plants or whatever, and us. And what do? Well, we crap. And that goes back down into the soil and then gets sucked up by autotrophs again. And so there's this little cycle of phosphorus that loops around between the autotrophs and the heterotrophs in biology. So phosphorus can get stuck in this biologic loop for hundreds of thousands of years, before it finally settles out into the bottom of the ocean. We find this phosphorus in soil, water, plants, animals. One of the consequences of this huge production of fertilizer that we have, both nitrogen and phosphate containing fertilizer, is that a lot of this phosphorus can get stuck in watersheds, fresh watersheds, all right? And it can lead to algae, the growth of algae. So this panel in the bottom here, this is pond scum. Does anybody live on a lake or have a lake they visit a lot? And as an animal or swam in a lake that had a lot of like green algae in it, chances are pretty high that that lake didn't look like that 50 to 100 years ago. Probably not even 15 years ago, 20 years ago. It often is accumulating phosphorus. And the thing about phosphorus is it's hard to get out of a watershed. It moves super duper slow. So even for this fast P cycle, it can be thousands of years, right? It can get stuck in this loop. Well, who cares about green algae in our lakes and streams and rivers? What do you think the problem with that is? I saw him first. What's up? Okay. All right. So has everybody heard of what he's talking about? What do we call that? Hypoxia, right? Hypoxia. It sucks the oxygen out of the water. So here is another map of the United States, and coincidentally, this area that's lit up here is roughly the same part of the country that got lit up when I showed you the nitrate contamination, didn't I? This is also where we have the highest input of phosphate into the green is indicating farmland, which are phosphorus inputs. All of this stuff dumps out right there by New Orleans and leads to these massive hypoxic zones in the Gulf of Mexico. They're all over the world. This is not just an American problem. Any place that there's a large watershed that has a lot of agriculture on it, where we're growing food, has these hypoxic zones offshore. The problem is it kills off the fish. So let me color that in a little bit for some of you who may not be following exactly how this happens. Phosphate makes the algae bloom up in these streams and rivers. It gets washed out to the ocean, the algae eventually dies, right? Because it's freshwater algae, gets washed out to the ocean, it dies, and as it dies, it gets eaten up by bacteria in the water column, which consume all of the oxygen in the water column as it degrades that algae that's settling out of the water column. As it sucks up the oxygen, the fish no longer can breathe in the water, right? Because fish don't breathe water, they breathe oxygen. It's in the water. Okay. Has anyone ever seen a fish kill anywhere before? I'm from Michigan. I've seen fish kills out on Lake Erie. Happens there. All right. So are we getting there? Oh, we're there. That's it.